Hi everyone! In the previous video we have explained the main characteristics of the balanced star connection. There you have a representation of this type of connection with the three-phase conductors, the three generators, the load which is connected to each phase of the system, and then the neutral conductor for the return of the current from this point N prime up to this other point N. Here you have a representation of another system which has a star connection. You have the star connection in the three generators and the three loads. So there you have the representation of the phase conductor, here this is phase R, between this generator and this load, and the other phases are S and T. Between this point, which is the start point of the generators, and this other point, we have the neutral conductor. When we have a balanced star connection, the currents IA, B, and C are called line currents, and they are going to have the same value as the currents which we call the phase currents. The phase currents are the currents that are passing through the loads, and in this case their value is exactly the same as the line currents. Here we can see how the current which is generated here in this generator A will flow through this phase conductor and pass through this load. So the value will be the same for the line and for the phase currents. As we have already said, the neutral current is going to be the sum of all the phase currents, and we are going to use the sign criterion of positive when it goes from the load to the generator. So when the system is symmetrical, that means that the three voltages in the generator, they have the same value. We are talking about the absolute value of the phasor, and they are shifted an angle of 120 degrees. That means that our system is symmetrical. When the load is balanced, what we have is that the load connected to each of the phase conductors has the same impedance in absolute value, and the angle is also the same. So, if the two previous requirements are accomplished, then we are going to have that the sum of the three currents, which is the current in the neutral, is 0. In that situation, we could even remove the neutral conductor from the system because the current flowing through it is going to be 0. Here in this expression, we have applied the Ohm's law to the first load. So we have the difference in potential between the two sides of that voltage divided by its impedance. This difference in potential is going to be the same as the difference between UAN minus UN prime N. Let's go back to the figure to see that. Here the difference in potential between A prime and N would be the same as the difference in potential between A and N minus the difference in potential between N and N prime. If you do that difference, you are going to get the same value as the difference in potential between these 2 points. Analogously, we could do the same with line currents B and C. As we have that the sum of the currents is 0, we can sum these three expressions, these three fractions, and the result should be also 0. Here, if you see, we have three terms in the numerators of the fractions that are equal. So we could group those three terms and express it like this. So 3 times the difference in potential between N prime and N divided by the impedance. So we have these two fractions which are equal to 0. As you can understand, we can have one of the terms at each side of this equation. So then we should have this fraction should be equal to this fraction with a positive sign. So, as you can understand, this fraction is 0. Why is that? Okay, because here we have the different values of the line voltages, and as you know, we started saying that the system is symmetrical. That means that the three absolute values of these phasors are equal and they are shifted with an angle of 120 degrees. So that's why the sum of these three phasors is 0. As we had two terms at both sides of the equation and this term is 0, that means that the other term should also be 0. So with that we can demonstrate that the difference in potential between points n and n prime is 0. So what are the implications of this? That these points, which are the two sides of the neutral conductor, they are going to be at the same potential, although they are not connected. So when we have connection star-star or y-y, if we don't have a neutral, we can pass from 6 conductors, which were the 3 phases and their 3 neutral conductors, to only 3 conductors, and with that we decrease the economical cost of the system. However, if we don't have the neutral conductor, any opening of one of the phases will produce an imbalance at n prime, and that will also cause an imbalance in the voltage of the two other phases. The consequence would be that one voltage rises over the expected value while the other decreases, and that will produce some problems in the system. That is why it is always advisable to use a neutral conductor. In this section 2.6, we have the equivalent single-phase circuit. The meaning of this is that although we are talking about three-phase systems, each of the phases has its own voltage, its own current flowing through the phase, and its impedance. So, at the end, we can treat each of the individual phases as a single-phase circuit, only if we know the correspondent value of the current, the voltage and the impedance. We can apply the Ohm's law there and obtaining the values that we need. Section 2.7 is about the delta connection. The delta connection is another typical connection that we can have in three-phase systems. In this case, the single-phase loads are connected between two-phase conductors, instead of the situation that we had in the star connection, in which the load was connected between one phase and the neutral conductor. So here, for example, load 1, it is connected between conductors A and B, between phase conductors A and B. The consequence of that is that the line currents A, B, and C do not coincide with the phase currents I1, I2, and I3. They do not coincide anymore, because here you can think about this node. In this node we have IA entering and I3 entering, and I1 which is flowing outside that node. So we can apply here the first Kirchhoff's law and then find the relationship between these three currents. But you can understand that they are not going to be equal. IA is not going to be equal to I1. In this situation, you can also understand that the difference in potential to which each of the loads is subjected is also different. For example, this load, the load which is connected between phases A and B, is going to be subjected to a difference in potential VAB. So in this case, the values of the phase voltages and the line voltages are also going to be different, and there will be a relationship of square root of 3 between the modulus of them. Here, if the load is balanced, what we have is that the three impedances, they have the same value. And then the three-phase currents in the load, they will be I1, I2, and I3. So the phase currents could be obtained by dividing the difference in potential between the two sides of the load connection by the impedance of the particular load. So then you can apply the Ohm's law to this branch here by taking into consideration the difference in potential and the impedance of this load. In that situation, the line currents can be obtained from the phase currents as follows. Current IA, we have applied the first Kirchhoff's law to the node that we have mentioned before, so we have this difference in currents. Current I1 would be difference in potential between A and B prime divided by the impedance of the load, and current I3 would be difference in potential between points C prime and A prime divided by the load. If we introduce the values of the angles and the absolute values for those voltages, we get to this result for line current A. We can do the same with current B to calculate the difference between phase currents 2 and 1, which are going to be this difference in potential between the impedance. This difference in potential divided by the impedance would be current 2, and this difference in potential divided by the impedance could be current 1. So then we get to this result. Regarding line current C, we would have the difference between current 3 and current 2, and we will get to this result. Consequently, we can express the value of the line currents depending on the voltage that we had. This is the absolute value of the phase voltage multiplied by 3 and divided by the impedance, and that with the correspondent angle here, expressed in polar notation. So here you have a complete phasor representation for the delta connected system, where you can see that the angle between the phase voltage and the line current is phi. Phase voltage and line current, they are shifted with an angle equal to phi. You can see that the phase voltage and the line voltage, they are shifted with an angle of 30 degrees. You can see that phase voltage A and line voltage AB, they are shifted with an angle of 30 degrees. And you can also see that the line current is shifted an angle of phi with the phase voltage. Here you have the explanation of the diagram. With all that information, now we can solve example 2.
In example 2 of lesson 2, what we have is an installation in which a balanced load is connected in triangle, that is load 1, and another balanced load is connected in a star. They say that the line voltage UAV is 400 volts and that we should consider UA, phase voltage UA, as reference phase. Taking that consideration, they ask the value of IA, that is line current A. What is line current A? Well, line current A is the line current here. If you understand this particular diagram, that line current is going to be divided into two currents. The first one will be current 1, which goes to this triangle to supply the sides of the triangle. And here it will continue IA minus I1, will continue here. And here we will have I2, which goes here to supply this load in the star. So we can then say that current IA is going to be the same as the sum of currents I1 plus I2. I2 could be directly obtained because the difference in potential between this point and this point coincides with the phase voltage. So I2 could be obtained directly by applying Ohm's law to this load, dividing voltage A by impedance 2. But what happens with current 1? Current 1 is not that simple, because here current 1 will arrive to this node, which is node A prime, and there we will also have current 3 and current 4. I have chosen an arbitrary sense for this triangle, okay, which is this one. So I have given a particular sense to the currents in this node. If we apply the first Kirchhoff's law to this particular node, what we have is that I1 plus I3, which are the currents entering into the node, they should be equal to I4. Then, here, current 1 could be also expressed as the difference between current 4 and current 3. And that simplifies the first expression, current A. Remember that line current A was a question of this example. This simplifies this expression because I1 can be substituted by this expression here. So we have I4 minus I3 plus I2. This will be the way in which we are going to obtain line current A. So now we need to calculate each of these currents. The easiest current that we can obtain is current 2. How do we obtain I2? By applying Ohm's law to this impedance connected in a star. So I2 would be the voltage divided by the impedance. First of all, we need to express this impedance in polar form. Its absolute value will be this, which is 14.14 approximately, and its angle would be arctangent of minus 10 divided by 10, which is minus 45 degrees, okay? So then you have 230. Well, why is this 230? Because the phase voltage is equal to the line voltage divided by square root of 3. So 400 volts, that was in the statement, divided by square root of 3 is approximately 230. We are considering this voltage as reference, so then 0 degrees. And in the impedance we have 14.14 and minus 45 degrees. So their result will be 16.27, 45 degrees amps. So by now we already have current 2. Now we need to obtain currents 4 and 3. So the problem with these currents are the currents flowing in the sides of this triangle. Let's start with current 3. In this side of the triangle, what is the difference in potential? Well, I have expressed here C prime and A prime. I have named the nodes as C prime and A prime. So the voltage would be UC prime minus UA prime. So what is UC and UA? Well, UA was 230, 0. And what about UC? Well, the reference that we are using is, this is UA, this is UB, that is 230, 120 volts, here 230, 0, and here UC is 230 minus 120 volts. So, there you have to do the difference, to calculate the difference between these two phasors. I am not going to write the change from polar to binomial notation, okay? But as you know, you have two options. Or you can introduce this in your calculator, and your calculator, if it is able to work with polar numbers, it will give you the result, okay? Or, on the other hand, you can pass this, transform these phasors to binomial notation, then do the difference, and then change again to polar notation. This is the same as voltage between C and A, okay? Line voltage between C and A. Well, line voltage between C and A is 400, 150 volts. So that is the voltage that we have in this side of the triangle. So then we can get the value of current 3. Current 3 is going to be UCA divided by impedance. In this case, it is called impedance 1. So now we need to change impedance 1 to polar notation, because we already have a numerator of this expression, but we don't have the impedance. In order to express impedance 1 in polar notation, we need its absolute value, which is this, and whose result is 42.43 ohms. And you also need the angle, which is arctangent of 30 divided by 30, so that is 45 degrees. So then you can introduce that here in ohms, and the result for current 3 is going to be this, 9.43 105 amps. So now we have currents 2 and 3. What else do we need? Okay, we need current 4. In order to get current 4, we need to know what is the voltage in this side of the amp. In this case, this voltage is going to be voltage A prime minus B prime, which is the same as line voltage AB. And that should be divided by impedance. Well, the impedance, we have already changed the impedance to polar form. So this is the impedance. And now, what is the value for UAV? Well, that would be the difference between UA and UB. 230, 0 minus UV, it was 230, 120 volts. The result I have is 430 volts, and you can introduce that here. And that will give you the result for current 4, which is 9.43 minus 15 degrees in amps. So now we have current 2, 3 and 4. Now that we have the 3 currents, to finish the problem, we only need to do that calculation, okay? So, I4 was the current here, okay? And was 9.43 minus 15 amps. I3 was the current here, and its value was 9.43105 plus I2 was the current here in the star connected load, and its value was 16.2745 degrees. If you assume that, you are gonna get this in binomial notation, which is approximately the same as 23 hours. So there you have